So far, we have been looking at a processor from the software point of view up to the interface with the hardware. We have, in the beginning of the course, talk about an addition, for example, or subtraction. And we did that thinking of them as instructions that are executed by the processor. We have understood that to execute an instruction, the processor has to take the value of the program counter, put into the address bus. The memory will fetch the word that is in the corresponding address, send back to the processor. The processor will put that address, word into the instruction register, and will decode that and figure out that an add instruction has to be executed. But how exactly the addition happens inside the processor? So when I say that the arithmetic and logic unit has to perform the addition, how does the arithmetic and logic unit performs that addition? And that is what we're going to be studying today in this lecture. So the first thing that we need to do to understand arithmetic for computers is we need to know that we are working, that there are operations that are done with integers. So we have so far in the course talking only about integer operations, so addition and subtraction, for example. We can also do multiplication and division. In this unit, we're going to start talking about multiplication and division, but we have not discussed that so far extensively in Teaching 9. And when I do operations with integers, one of the things that I need to be concerned about is that sometimes the result of the operation may not fit in the number of bits that I have to store the result. And in that case, I have something that's called overflow. We're going to be discussing overflow in this unit as well. But this is only part of the operations that the computer does. The computer also has to deal with real numbers. And for real numbers, we use a representation called a floating point representation. In subsequent lectures, we will be discussing the floating point representation for numbers. And we're going to be looking at both the representation and the operation for numbers in floating point. But today what we want to do is to focus on addition. And to focus on addition, we will start by the simplest of additions. That is, how do you add two bits together? So if I have 2 bits and I want to add the value of those 2 bits, I will obtain 1 bit that's the sum of the 2 bits. So if I add 0 to 0, I obtain the sum equals 0. And I also always have a carry bit. In this case, the value of the carry bit is 0. If I add 0 to 1, the sum is 1, and the carry bit will be 0. If I add 1 to 0, it's the same result. The sum is 1 and the carry bit is 0. And if I add 1 to 1, then the sum is 0, and the carry bit is 1, because 1 plus 1 is 2, so the 1 gets carried and the sum is 0. So those are the 4 possible results that I can have if I want to add 2 bits. And the circuit that I use to add 2 bits is the circuit that I'm showing here, where I'm using gates, and the gate on the top is the XOR gate. So here is the XOR gate, and as we already understand from the XOR instruction, what the XOR gate does is, if the 2 values in the input of the XOR gate are different, then the output is 1. If the 2 values are the same, the output is 0. So we can come here in our examples and see that when the 2 bits are the same, they are both 0, the sum is 0. Or if they are both 1, the sum is also 0. So by doing the XOR of the 2 input bits, here A and B are a single bit value, I obtain the sum value. For the carry out, I can check and see that the only situation where I have a carry out equal 1 is when both bits are equal 1. So the logical operation to obtain the value of the carry out for this single bit operation is the AND operation. So the sum is 1 when A and B are different, and the carry is 1 when A and B are both 1. So that was the circuit for addition, but in general what I needed to do, and that circuit is called a half adder because it only adds 2 bits. But in general what I need to do is to add 3 bits together because I need to add the 2 bits for the position in which I'm adding plus the carry that came from the previous position. So the actual adder that makes sense to me in a computer is what is called a 3-bit adder. That is, I have 3 inputs. So in that case, what happens if I have 1 plus 1 plus 1, the result is 1 and there is a carry of 1. If I have 1 plus 0 plus 1, then the result is 0 and there is a carry of 1. If I have 0 plus 0 plus 1, the result is 1 and there is a carry of 0, and so on. If all zeros, I get 0 and 0. So what's the circuit that I'm going to build to build my what is called a full adder? That's an adder that adds 3 bits together. So if I look at the inputs A and B, that will be the 2 inputs in the top, I still have the same thing, that the A and I will have an XOR gate to tell me whether A and B are different. So at this point, all I know is that A and B are different. So the only place where that output will be 1 will be this one, where if I assume that my top bit is A, my second bit is B, this will be the only place where I have a 1. Or actually in the slides what I assume is that A and B are the lower 2 bits, which makes sense because I want the carry to be the top bit. So in this situation what I have is that this in this case and in this case they are different. And now I'm going to take the value of A and I'll AND with the value of B. And this will tell me that A and B are both 1. So the only situation here where I have A and B both equal 1 is where I have the 1, 1 input. So I have those 2 values now. I know when A and B are different, and I know when A and B are the same. I need to combine with the carry. So now I'm going to take the carry in, and I will do an XOR with this bit that I have here. So remember, the only position where A and B were different were this position and this position. Now, the A and B being different here, 0 or XOR 1 will make 1. Now I have 1 XOR 1 here. So that will make this into a 0, which is the result of the sum. In this case, I have 0, 1 here, so this makes the XOR equal 1. And then I do an XOR with a 0, and and in my result is a 1. So that gives me the value of the sum. And so this tells me that one of these 3 inputs are 1. Not 2, but at least one of them. Sorry, 1 or 3. So in this case, if I have this situation here, I end up with a 0 because I have 2 inputs. In this situation, I have 1 input equal 1, so I end up with a 1. What happens in this situation? In this situation, if I do an A and B, XOR of A and B, that will gonna give me a 0. And then I do an XOR of this 0 with that 1, that gives me a 1, and that's what I have here. So what this circuit here is telling me that I have 1 or 3 inputs equal 1. This is also called the parity circuit because it tells me whether the number, I can look at the output and know whether the number is odd or even, if the number of ones is odd or even. So this is the situation where I get a 1, and that's the sum. Now what I'm going to do, I will take the same A and B output and I do an AND with the carry in. And then I'll do an OR of these 2 partial results here. So what I have in the end is that at least one of the 2 inputs are 1 in this case. Because look, if A and B are both equal 1, I get a 1 here, and that will cause the output to be 1. The other situation that I can end up with a 1 is if at least one of A and B is equal 1, because they have to be different. So one has to be 0, the other has to be 1. and the carry in is 1, then I end up with a 1 in this line. In a 1 in this line will pass to the output, because what the OR does is if either one of those input is equal 1, the output will be equal 1. So that will gonna give me the value of the carry out, and I will have a 1 if at least 2 of the inputs is equal 1. So you can see that in this case I have a carry of 1, otherwise I have a carry of 0. So this circuit altogether can give me both the sum in this line, so the bit in the bottom, and the carry out, that's the bit that I have over here, with this circuit. So what I'm going to do now is I will encapsulate this entire circuit into a box. So imagine that I have a box that contains exactly that circuit there. So this box has 3 inputs, has 1 bit input A, another 1 bit input B, and a 1 bit input carry in. And this circuit has 2 bit outputs. 1 bit output will be the carry out, and the other bit output will be the sum. So you can imagine that I took that circuit that I explained to you, and I put that entire circuit inside this box here, and this box now is what is known as a full bit adder, or a 1 bit full adder. So the other way that I can look at this circuit is to look at all the possible combinations between the carry in A and B, and do the truth table here showing me what is the result supposed to be, and look at the truth table, I can tell when the value of the sum should be 1 and when the value of the carry out should be 1. So this is what that box implemented. But of course, I don't want to be adding a single bit. My register has 32 bits. So how do I add all the 32 bits, or how do I add multiple bits together, a number that has more than 1 bit? So to do that, what I'm going to do initially is what I call a ripple carry adder. What is a ripple carry adder? It is, I take one of those adders and I connect the carry out of my first adder. So there I have the carry out of the first adder, and now I will connect to the carry in of the next adder, and I will repeat this process for however many bits I want to add. So in this example here, I have I think I finish with, so I can go all the way to 31. So if I want to do a 32-bit adder, because remember, if I'm adding T0 to T1, I'm adding 2 32-bit numbers, I can use this circuit to do the addition. And what I have now is that in the end, I'm going to get the 32 bits for the sum. And remember that in the case of the addition, most of the time I can simply ignore the carry out if I get the carry out in the end. And we're going to see when that happens and what we do to detect that we had a problem with the representation. However, now we need to stop for a minute and we need to think about what's going on. When I built that circuit before with the gates, the propagation of the signal from the input of a gate to the output of a gate is not 0. There is a time delay between the time that I have the stable signals for the inputs, for the bits in the input, and the time that I get the output. So now if I consider this circuit, and I could give you numbers, but just for the for the sake of we thinking here, let's say that I take 1 unit of time to propagate the signal from the carry in to the carry out of one of those boxes. So the question is, how many units of time do I need to do the 32-bit addition? And of course, if we start looking at the propagation, what we're going to see is that we need to consider the longest path through the circuit. So if I take this approximation that takes 1 unit of time for me to propagate from the inputs to the outputs of this box, what I'm going to see is that if at time 0, I have all the values for all the inputs on the top, and I have the value for the carry in, at time 1, I would have this sum completed, and I will have this carry out completed. But I cannot complete this sum at the end of time 1 because I did not know the value of the carry in for that box. So at time 2, I could complete the second bit. At time 3, I can complete the third bit, and so on. So it would take 32 units of time for me to be able to obtain my 32-bit sum here, because I need to wait for the longest path. The longest path will be for this carry in to propagate all the way through the 32 bits to get to this S31. The problem with the situation is that this propagation delay is too long for us to be able to do computation at the speed in which we want to do the computing. So we need to do something to speed up this process. And the way we're going to speed up this process is by doing something that we call the carry look ahead adder. So I'm going to stop the recording here, and then I'm going to discuss the carry look ahead in the second part of this lecture.